Hello and welcome to The Daily Space. I'm your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we are here to put science in your brain.
Today we are pleased to bring you a special guest, Dr. Gail Christeson from the University of Texas, Austin at the Institute for Geophysics. She is the lead author on a recent paper mapping the Chicxulub impact crater. But before the interview, let's look at the news.
As a space news show, we are able to spend most of our time happily ignoring global politics, economics, and stories related to human beings other than scientific stories and how they act. We can't always do that, however. And in today's first story, we are reminded that rockets are really no different than missiles, and both can do harm far more easily than they can do good. Early Monday morning, November 15th, Russia launched a missile from the Plastek launch site on a trajectory that would intersect the orbit of the defunct Cosmos 1408 satellite in low Earth orbit. This was a test of Russia's anti-satellite launch capabilities, and it was successful. The 2,200 kilogram former surveillance satellite was reduced to a cloud of debris with over 1,500 trackable pieces. This expanding cloud of shrapnel intersects the orbits of both the International Space Station and China's Tiangong Space Station. While it is unknown what actions may have occurred on the Chinese space station, U.S. and Russian astronauts took shelter in the Soyuz and Dragon capsules, which are more robust than the typical space station module. NASA Administrator Bob Nelson is quoted as saying he believed the Russian Space Agency didn't know anything about this, and per the New York Times said, and I quote, "Had any of those known about it, they should have been raising Cain because of the threats to the astronauts and cosmonauts on the space station." End quote. As of Tuesday morning, the astronauts had returned to the International Space Station from the capsules, but were continuing to keep doors closed between capsules to reduce the possibility of a collision causing complete loss of the station. The International Space Station is passing through the debris cloud roughly once an hour. In addition to creating a direct threat on the lives of the astronauts on the International Space Station in Tiangong, this debris is also going to endanger all the other missions orbiting in low Earth orbit, with Starlink satellites included in the mix. This is perhaps the definition of a hot mess in orbit, and satellite operators around the world are watching as tracking solutions come in. This is just the latest in a steady stream of nations showing they have the capability to destroy satellites. In 2007, China destroyed a 750 kilogram weather satellite and created more than 3,000 detectable pieces of debris. In 2008, the U.S. destroyed a defunct National Reconnaissance Office satellite, creating 400 pieces of trackable debris. And India performed a similar scale test in 2019. It is difficult for the U.S. to condemn another nation for doing something we have already done, but the U.S. has condemned Russia's actions. The timing of this particular test is troubling. The number of satellites in orbit has vastly changed since the U.S. and China tests in the 20-aughts. This new test is taking place with vast numbers of Starlinks, OneWeb, and other satellite internet constellations in orbits intersecting with the debris. While this particular incident is unlikely to trigger a chain reaction of collisions, an effect named the Kessler syndrome, a great deal of orbital maneuvering is going to be needed to avoid collisions, and that will use up fuel and shorten the life expectancy of spacecraft. Political watchers also point out that this test occurred at the same time that Russia has built up troops on their border with the Ukraine. As a Gen X kid who read far too much Tom Clancy, I have to admit this scares the pants off me. Hopefully this was just a flex, and the worst that will happen in the coming days and years is a shortened life for some of those easy-to-replace Starlinks.
We had originally planned to cover some climate change news today, but we've decided new updates on planetary problems can wait. Instead, let's imagine an amazing star system in which a large hot Jupiter orbits a pair of stars. This terribly named system, TIC 172900988, is the first system in which a planet has been observed to pass in front of two different stars during a TESS observing run. The TESS mission observes different regions of the sky for 27 days at a time to look for planets transiting in front of their host stars. During these transits, we receive slightly less light in a distinctive way that is consistent with a round object slowly moving into and out of the light of a star. To confirm that we're seeing a planet and not a deceptive star spot or other phenomena, astronomers want to see three transits spaced out in a way consistent with a world circling its star. With just a 27-day window per observing set, TESS can only do this for worlds on exceedingly tiny orbits or in very special cases. And it turns out one planet passing in front of two stars is one of those special cases. The two stars in this system are both about 30% larger than the Sun, while the planet appears to be about the size of Jupiter. While the entire orbit of the planet takes less than a year, it only took the planet 5 days to go from blocking the slightly larger star to blocking the slightly smaller star. But in itself, these transits are only enough to say there is probably something there. But it isn't enough to say there is definitely a planet there. And this is where data archives are so important. This paper is published in the Astronomical Journal with lead author Veselin Kostov, and the paper's abstract notes. Archival data from Assassin, Everyscope, Kelt, and Superwasp reveal a prominent motion of the long axis of the binary orbit caused by the dynamical interaction between the binary and the planet. The stars orbit in an ellipse, and over time, the planet changes the alignment of the ellipse and reveals itself even when we can't see it. Luckily, thanks to some art, we can at least imagine the system with one Jupiter-sized world orbiting two hot, bright stars. After the break, we'll be back to take a look at solar systems and things they fling around.
In the past decade, we've developed amazing capacities to directly image planetary systems forming around young stars. With the Atacama Large Millimeter Array in particular, we've seen amazing systems with delicate ring structures that sometimes even have knots of material thought to be planets. It's the sometimes in that statement that is a bit troubling. We like to think that planetary formation is a nice, clean process. Giant molecular cloud starts to collapse and fragment. The fragments will spin and flatten as they collapse, with a star taking shape in the center and planets cleaning out rings in the disk as they gather up their own mass. Over time, the star will brighten and push out leftover remains. The system will be left with however many planets, maybe an asteroid belt, and icy stuff in the outskirts. It's a nice picture. It is also overly idealistic. Solar system formation is a violent planet-hit-planet kind of process. And thanks to a new paper in the Astrophysical Journal, and led by Kazuhiro Kanagawa, we are learning that the gravitational interactions between newly formed planets and their surrounding rings of unused material migrate planets into the centers of gaps where we may not see them. This work was done using supercomputers to simulate all the motions of gas, dust, and forming planets in a variety of systems. And the simulations evolved those systems to match actual systems observed by the Atacama Large Millimeter Array. 3 different planet and ring stages were uncovered in these simulations. And here I quote from the National Astronomical Observatories of Japan release. In phase 1, the initial ring remains intact as the planet moves inwards. In phase 2, the initial ring begins to deform and a second ring starts forming at the new location of the planet. In phase 3, the initial ring disappears and only the latter ring remains. These results help us understand why planets are only rarely spotted interacting next to rings. Unfortunately, we are only able to really see the outer parts of disks clearly and resolve different structures at great distances from stars. It is hoped that the next generation of space and ground telescopes will allow us to understand the inner workings of systems more and verify that our simulations match the reality of planet formation at all distances from a star.
One of the weird fallacies of our knowledge of the solar system is the idea that the Earth only has one moon. Wait, what? No, it's true. The Earth has other natural satellites than the moon. They're not on the same order as the moon, though, so they're called quasi-satellites. And Earth currently has 5 of them. We say currently because these bodies are small and usually have orbital characteristics that deteriorate until the tiny moons escape the Earth's gravity well. Of the 5 quasi-satellites we know of at the moment, the one with the most stable orbit is Kamo'oalewa, a 50-meter diameter near-Earth object with a rapid rotation of 30 minutes that can come within 14.4 million kilometers of our home planet. And while its orbit is stable-ish, the geometry of the orbit with Earth makes it difficult to observe. A team of researchers have collected about 5 years worth of observational data from the Large Binocular Telescope and the Lowell Discovery Telescope. They collected both photometric and spectroscopic data in the hopes of understanding Kamo'oalewa. What they found is spectral characteristics that show silicate minerals, the stuff that makes up most of the rocks here on Earth and other rocky bodies, as well as a bunch of space weathering. Planetary Science Institute Associate Research Scientist and co author Juan Sanchez explains. This means that the optical properties and physical structure of the surface have been modified by micrometeorite bombardment and solar wind particles. Then, when the team dug even more into the spectroscopic data and compared it to the spectra of meteorite samples and other near Earth objects, they found similarities between the spectrum of Kamo'oalewa and a lunar sample collected during the Apollo 14 mission, which means, interestingly, that this temporary moon could have come from the moon itself, possibly as ejecta from an impact. It could also have been simply captured by the Earth's gravity well from the rest of the near Earth asteroids. The team is now planning for a sample return mission to Kamo'oalewa with a possible launch date in 2025. After the break, we'll be back with Dr. Gail Christeson to talk about mapping the Chicxulub impact crater off the coast of the Yucatan Peninsula. Stay tuned. Welcome back, everyone. Joining me now is Dr. Gail Christeson, a senior research scientist at the University of Texas, Austin, and associate director of the university's Institute for Geophysics. Dr. Christeson has focused her research on crustal structure of various geological environments, including the formation and evolution of oceanic crust, the size and morphology of the Chicxulub impact crater, and the rifting history of the Gulf of Mexico. She uses wide-angle science and tomography and is the lead author of a recently paper in the Journal of Geophysical Research Planets, where she analyzed such data to map the Chicxulub impact crater. Thank you for joining us today, Dr. Christeson, and welcome.
Thank you. It's a pleasure to be here.
So tell us about the Chicxulub crater. Pretend that our audience knows very little and give them sort of a basic rundown of what it is and why it's important.
Okay, well, 66 million years ago, there was an impact on Earth, and that coincides with the mass extinction, which is mostly well known because of the dinosaurs. And at the extinction, there is a layer that's found worldwide that has iridium in it, and that's how we know that an impactor is linked with the extinction. So there was a search for where this impact crater could be, and eventually it was discovered that it's on the Yucatan Peninsula of Mexico, but it's buried because it happened 66 million years ago. So we use geophysical techniques to investigate the crater and to confirm that it actually was a crater to begin with.
So it was a very big deal when the crater was finally found. I remember the news stories and the excitement and watching a show on how it was found partially using oil company data that had been basically sitting around, and then finding the cenotes and the Yucatan Peninsula itself and sort of mapping it all out. What has been your goal with the mapping that you've been doing?
So I've been involved in looking at the Chicxulub crater for a long time. We were involved in one of the first studies that actually confirmed that it was a crater. But since then, we've been trying to understand more about this crater because it's the best preserved large impact crater on Earth. So trying to understand how large impact craters form. And this crater is what's called a peak ring crater. So when you have a large impact, you remove so much material that you get uplift, right? It's unstable. So you get uplift, and then that uplift becomes unstable and it collapses. And you end up with a ring of mountains that we call a peak ring. So in 2016, I was part of a team that drilled into the peak ring of the Chicxulub impact crater. So this was the first time ever that a peak ring has been sampled for science.
And what did you find in that peak ring? What was the big result there?
So there have been some different models about how peak rings form, but what we found was that the core of the peak ring is fractured granite. So this is material that was deep beneath the surface, maybe 10 kilometers, and it was uplifted and then collapsed to form the peak ring. But on top of the granite are some very unusual rocks. There's what's known as swavite, and this is the breccia that has impact melt. So when you have a large impact, you have so much pressure that you get pressure-induced melting. And so we sampled that impact breccia, and then also a little bit of melt rock as well.
All right, I want to talk to you some more about some of the physical properties, but first we're going to take a quick commercial break and we'll be right back. All right, welcome back, everyone. With me now is still Dr. Gail Christeson from the University of Texas, Austin, and we're talking about mapping the Chicxulub crater in the Yucatan Peninsula. You did some mapping as well. So what came out of the mapping? I know that I've seen the pictures of sort of the structure of it. What did you learn from the mapping that you've been doing?
Yeah, so what was exciting was we had already acquired geophysical data over the crater, seismic data. And then with the well that was drilled, we actually knew what was, underground. So what we were doing was mapping the subsurface so that we could take what we had learned at the well and map further into the crater. So, for example, we were able to find out that swavite, that impact breccia, is very uniform in the crater. And we had some ideas of how this forms, but because it's so uniform, it makes you think that it came all at once. It wasn't like a gradual event that happened and then filled in the deep parts first. It came and filled everything in all at once. So it must have been very energetic. And we think this was because of a tsunami that came back into the crater, is where most of that deposit came from.
So has this mapping helped you sort of create a timeline as to what occurred with the impact itself and the results?
Not so much a timeline, but more of a regional picture, because all we had was, like that one pinprick of the well. But the other really exciting thing that we found is we think we see evidence of hydrothermal circulation. So we know that with this large melt sheet that was formed, that there is hydrothermal circulation that's set up because there's water and the source of heat. And some of the rocks show that. But what we saw in our data further away from the impact from the well is evidence of upflow. So you can see things are disturbed at the edge of the melt sheet. So we think there's like a hydrothermal cell that was set up that we can actually see the edges of. So that was really exciting, and that was the first time we've seen something like that.
That's really interesting. I like that. Thank you so much for joining us. Is there anything I didn't ask you that you wish I had asked?
No, I think you covered a lot of material in a short amount of time. That was great.
All right. Well, thank you so much, Dr. Christeson, for joining us. And it was a pleasure having you here.
Okay, thank you. Goodbye.
This has been The Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of generous people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.